We move to secured RDTs by Sam, please.
All right, thank you. I am Sam van Vonder, and this is joint work with my colleagues Thierry, Renaux, and Wolfgang de Meuter. So this work is in the context of replicated data types, and this is a type of data structure that can be replicated to multiple peers in a network. So each copy is called a replica, and via the properties of replicated data types, their contents are automatically synchronized. So you can think of them actually like Google Docs, but for general purpose data structures. Nowadays, replicated data types are powerful enough to support standard JSON objects like these, which have a key x1 and some sub-object with the keys y1 and y2. And you would use replicated JSON like this in an application for two important properties, or at least properties important to me, namely offline availability and automatic merge conflict resolution. So offline availability means that when the network goes offline, each peer can independently continue to update their local object. For example, on the left, where a key x2 is added with a subfield A, and then on the right, where a key x2 is added with subfield B. And then automatic merge conflict resolution means that once the network connection is restored, then replicas will resume synchronization, and the properties of RDTs guarantee that eventually the objects converge to the same state. So in this case, merge conflicts on the key x2 may be resolved by merging the objects and keeping both keys A and B. So in this paper, we use JSON replicated data types in the domain of web applications, where synchronization is mainly between a client and server. So typically in web applications, there is a trusted application server, and the clients cannot be trusted because they can easily tamper with their local application code. So for example, in the web browser console, they can easily tamper with it, web browser extensions, user scripts, or even cracked mobile applications. So we asked the question, what if the application, as defined by the server, has data security constraints? So in the paper, we use a motivating example of a nature conservation organization like Belgium's Nature Point, which uses volunteers for the upkeep of forests and parks. And when such a nonprofit wants to find out what plant or animal species are present in a forest, then they develop a mobile app that can be used by volunteers to take pictures of plants and animals and categorize them. So the nonprofit is run entirely on volunteers, so they contact the local youth organizations, they put them into different teams and send them into the forest. And so usually this kind of crowdsourced observations includes some gamification mechanism where at the end of the day, the team with the most points wins a prize. So therefore, the company also uses an expert biologist to award points to teams based on what they cataloged. So offline availability is very important for the user experience of this application. So on a technical level, the company may choose to use replicated data types and store their application in a application state in a big JSON object. So for example, this object with the data of team blue at the top and team red at the bottom. So each team has some data like a name, some sightings. Each sighting is tagged with the key being a large number, so a timestamp, a Unix timestamp. It has some locations, species, photo, and perhaps some points and feedback awarded by a biologist. So the application also has security requirements, and I listed them here in natural language. I won't go into detail into each and every one of them, but it includes things like the red team should not be able to see the locations of the blue team sightings or vice versa. And for example, the blue team, once they have been awarded some points, they shouldn't be able to arbitrarily increase those points and so cheat at the game. So this should not be possible. I mean, this is just a didactic example, of course, but it generalizes to any situation, for example, in business applications where different users have different access to data. Now, when you want to use the current state-of-the-art in replicated data types for this kind of application, then we find that the following problems occur. So namely replicated data leaks, data contagion, and the lack of offline policy enforcement. So replicated data leaks means that read privileges cannot be enforced, because currently with replicated data types, each user is sent a full copy of the JSON data and any updates to that data. So for example, locations will be leaked. The next problem is data contagion. So since malicious clients cannot be prevented from making local changes to the data structure, because they can bypass any local security, then whenever such malicious changes occur locally, then currently in the state of the art, they are simply synchronized to the other peers, and they will gladly accept those changes as valid. So for the last problem, a developer cannot implement security checks in a typical way by contacting the application server, because then the application no longer works offline. So to counter this lack of offline availability, the clients really need to be able to locally check while they are offline what is allowed and what is not. So our proposal to solve these issues is called Secure RDTs, or SRDTs for short, and in the paper we specify them as an operational semantics engineered in PLT Redux, but by now we also have a proof of concept implementation as a wrapper for the auto-merge library. So let's start with some base assumptions. SRDTs assume that all clients are untrusted and that there is a trusted application server which we call the leader. So typically this would be owned by the company, like the nonprofit. So compared to the state of the art on data replication, we no longer allow peer-to-peer synchronization, so only between client and server, but we retain the desirable properties of offline availability and automatic merge conflict resolution. To preserve offline availability, each client must be able to locally check the security policy, but since we cannot enforce that they follow this policy, we additionally require leader-side enforcement to ensure that no data is leaked to clients and that no data is maliciously modified. So for the rest of the presentation, SRDTs can be explained in 4 steps. So first, we need some way to specify a machine-readable security policy for JSON data. Next, we need to make the security policy available offline, which we do via security policy projection. Third, we need to enforce read privileges, which we do via data projection. And so finally, we need to enforce write privileges when synchronizing changes. So the first step of the solution is for the leader to specify a security policy that grants a user access to a part of the document. And so since data in a document is stored in the leaves, which I have highlighted in yellow, and since this document is highly dynamic, so it can continuously grow or shrink, we use so-called path selectors to select potentially multiple leaves of the document at once. So path selectors are inspired by JSON path, and this is like XPath, but for JSON documents instead of XML documents. These path selectors support traversing the object based on an exact key match, a wildcard to match any key, or more programmatic predicates based on keys, one of which I will show later. So for example, the second rule of the security policy says, not of the security policy, of the motivating examples security policy, says that biologists can read the sightings of all teams. And so these 2 path selectors here, they select the fields that would correspond to this security policy. So for the first path selector, the yellow wildcard says that any key on the top level is allowed to be traversed. This must be followed by a sightings key, which is present in the object, then followed by another wildcard to traverse any sighting made by the users. And then for the top path selector, finally, the leaves which are selected by a wildcard are highlighted in blue. And then for the bottom path selector, it traverses 1 level deeper, namely via the location key, and it selects all of the fields highlighted in green. So using path selectors, the security requirements in natural language can be translated to code as a list of rules to allow some role read or write permissions of a particular set of fields as identified by a path selector. And by using programmatic JSON path operators on keys, the security policy can select parts of the document based on a user's properties, like, for example, being a part of Team Blue or Team Red. Now, the second step of the solution is to project the security policy in order to get a security policy excerpt for each role. So each excerpt only contains the privileges that apply to a specific user, and we do this because in some cases, even knowing that certain data exists can already be a security concern. So in the motivating example, this means that from the full security policy, we make two excerpts, namely for the user role and for the biologist role, and these policy excerpts can be used to send to the client to locally check whether an operation is allowed when the clients are offline. In the third step, the security policy excerpts are combined with a user environment, and this is like a set of properties about the user which are defined on the application server. It is combined with the policy excerpt to create a projection of the application data. So in the motivating example, since the blue user does not have read access to certain fields of the red the data about the red team, the striked out fields will be removed from the object before it is sent to blue users. So similarly for red users, in this case they have the same role but a different user environment, and this results in a different projection of the data where different fields are removed from the data. So data projection ensures that read privileges, that malicious reads are no longer possible based on the security policy. And finally, when users write to the data structure, this must be checked at runtime by the leader. So the workflow of an application is as follows. First, a blue user logs into the data, to the server and fetches a copy of the data, and the server responds with a policy excerpt, projected data, and the user environment. Then as long as the blue user is well behaved, they can eventually merge their changes to the server and they will accept it. When malicious users make changes, they send them to the server and the server will simply reject them. And then when a user such as the biologist merges a change, a well-behaved change, that should only be visible for members of the blue team, then of course this change is only sent to blue users and not to red users who do not have the read privileges. So since it's important that the system is actually secure, we formalized it as two languages in PLT-REDX, namely replica lang models the behavior of each client and leader lang models the behavior of the leader. So these unreadable security rules, not security rules, the inference rules and reduction rules model that behavior. So in the paper we have proofs that based on the operational semantics that the problems no longer occur there, so that it has freedom from replicated data leaks, freedom from data contagion, and the availability of offline policy enforcement. Now the formal proofs are very nice, but once we started actually executing programs using PLT-REDX, we found problems, for example, in edge cases that needed to be resolved. So we basically generate programs with lots of random data and a random security policy, and then check that all read and write access is correctly enforced. And so we repeat this for many, many objects and security policies to gain statistical confidence that the operational semantics is actually correct. And so using this technique, we were able to remove bugs from the operational semantics, one of which included a security error due to an implementation mistake on our part. So on this note, I will conclude by restating the problem. So at the start of the presentation, I explained that with state-of-the-art replicated data types, it is possible to share JSON documents between a client and server. And these have desirable properties, for me, most importantly, offline availability and automatic merge conflict resolution. But as soon as developers want to impose access control on the data, then they run into replicated data leaks, data contagion, and the lack of offline policy enforcement. But using RDTs, replicated data leaks are solved via security policy projection and data projection. Data contagion is solved via runtime write enforcement. And the lack of offline policy enforcement is, of course, solved by making security policy excerpts available offline. So finally, if you want to experiment using RDTs, do check out the paper and our reusable artifact. Thank you.
First off, I have a small question. Do you assume a static or a dynamic group membership?
Currently static, as in the security policy cannot change at runtime.
Okay, so why do you need the central server then?
Yeah, that's fair. Well, for one, to keep a, let's say, master copy of the data. Because we assume that in a web-based setting, the clients connect to a server and then load basically the entire application state and, well, data security policy and so forth.
But then it wouldn't need to be authoritative, right?
Sorry?
It wouldn't need to have any authority then, if you just only have it as a backup, right? And
well, it still needs the authority, as in it is a single source of truth, namely a peer in the network that all clients trust. As in the clients, they can't synchronize peer-to-peer currently, but they would not be able to trust each other, so at least they can contact the server to provide that trust.
okay. So it's just simpler that way to implement a central server, but in theory it would also work in a distributed scenario, right?
Yeah. So basically, by doing it this way, it's extremely nice to implement applications using CRDTs and also segment the data or the CRDT based on the roles of the client. So it's a very nice way to implement it and guarantee it to be correct, no security programming mistakes and so forth.
I had the same question.
Hi, thanks for the talk. My question goes in a similar direction, and it seems to me that by using this central server, you use a lot of the benefits that CRDTs can give you in other cases, namely, for example, peer-to-peer collaboration. So that's not really possible in your setting. Is that something that you thought about at all, or that you would like to support at some point? And do you have some ideas what the challenges there could be?
Yeah, so indeed that is something that we'd like to support, but it's extremely difficult. As in doing it completely peer-to-peer devolves into encryption, key management, and, well, trust issues essentially. We think by doing a first step with a central server, we are able to provide a level of security that might not be possible in peer-to-peer situations. Being that the security guarantees will be different if you do it peer-to-peer or if you do it via central server. I think both approaches can exist at the same time. And so purely anecdotally, having a central server is not so academically pleasing, as in we like peer-to-peer and local first software and so forth. But in practice, there are big companies doing CRDTs in a centralized way where they explicitly do not want a central server. So Figma is the biggest example, I think, big company acquired by Adobe.
Okay, yeah, thank you.
Right.
Let's thank Sam again.